In this question, we're told about a square-based pyramid, P, which has vertices A, B, C, D, and E. The issue is that we don't know which point is where the point is. And we can't guess, we need to figure it out. And part A helps us, well, along the way to doing that. If we actually find the vectors A, B, A, C, and so on. Just a very quick reminder, we've got an origin here, and then we've got, say, a point A and a point B. Now, if we want to get from A to B, what we can do is we can go along here, which would be minus A, because it's going in the opposite direction of O to A, and then along here, which will take us B. So AB is actually equal to B minus A. We always take the second point, essentially, and minus the first point. If you not actually minusing points, but, in terms of the little vectors. So let's go ahead and do this. It should be quite quick. We don't need to, well, it depends. I mean, should we show all our working? You just need to be careful that you don't make a mistake, because one little mistake can just, cost us a lot later on. Okay, so 5 minus 2 is 7. 8 minus 3 is 5. Minus 6 minus 1 is minus 5. First one's done. Now let's do AC. It's going to be C minus A. So 4, 2, 4. AD is going to be D minus A, so it's going to be 8 minus 2, 2. To be fair, I can fit up here. BC, C minus B, so minus 3, minus 3, minus 9. BD, BD minus B, 1, minus 7, and 7. And then finally, CD is going to be D minus C, 4, minus 4, minus 2. Brilliant. In the second part of this question, we're asked to do lots of different things, including finding the length of a side of the square base of P. So at this point, we're going to need to find where all the points actually are. And we can do that by basically finding the lengths. That will allow us to figure it out. So I can use 3D Pythagoras here. And it's just doing lots of squaring and adding. So I get root 99. This one's root 36, so we actually get 6 as our answer. Okay, here it's another root 99. Actually, another one here. Finally, this one's going to be root 36 again, so 6. Right, I'm going to draw this square base pyramid again. The point up here. Now, if I'm along my square base, there's only like one other vector that's going to be like this will be the same as this, is what I'm trying to say. So the root 99 is a bit of a giveaway for what point is the top, because there are 3 points that go to B. B is the common letter in all of these, that have the same length. And the only way that this can be true is if B is at the top. And after that, it doesn't matter. Oh, wait, it might matter where we put the rest of them. So I've got this root 72 in there. That must mean that if A is here, then D is going to be diagonal, because root 72 is going to be bigger than 6. Then I can put in the others. So I can put C here, and then this one here will be the missing one, which I don't have, do I? So this one's going to be point E. Okay, I don't think it matters. We could swap those two around if we wanted to, because it would just be like rotating the pyramid. So that's absolutely vital. And we've also answered part 1 to this question, which was the length of a side at the square base of P is going to be 6. Next up, we're asked for the cosine of the angle between one of the slanting edges of P and its base. So we can pick one. I'll go with AB here. And then we'll have to do the dot product with AD. That will give us an angle between the slanting edge and the base. If you try and do AC, then you won't, for example, you won't get a right angle triangle that we will get here. You can see from this right angle triangle that this is the base. You'll get some other kind of triangle, and it won't actually be the angle between the base. So we need to do AB dotted with AD. And remember, when you do the dot products, you want the angle between them, so you need to have the two vectors pointing away from the angle. Well, first up, when we do it, we're going to do 7 times 8, 56. And then it will be minus 10 and minus another 10, which will give 36. And the second way the dot product is written, remember that's times in the components, is to times the magnitudes and then times by cos theta. So I've got root 99, I've got root 72, and I've got cos theta. So cos theta is going to equal 36 over, I can write this as root 9 root 11, and root 72 is root 2 root 36, which is going to be 36 over 3 times root 11 times root 2 times 6. The 6 will cancel partially with the 36 to leave me 6, and then the 3 and the 6 will cancel to leave me 2 here. And I could leave it like this, but actually 2 divided by root 2 is root 2, so probably the simplest answer is to write it as root 2 over 11. You could also write it as root 2 over root 11, of course. Okay, on to part 3, where we're asked to find the height of P. And then in point 4, we're asked to find the position vector of E. So I want the height. Well, I've actually made good headway with this because we've got the length AB, remember? Which was root 99. we have we want the height here, and yeah, I've drawn a right angle triangle already. I just need to label this something. Maybe I call it M for the midpoint of the base. So AM, the magnitude, is going to be a half of the magnitude of AD, because it's the midpoint. And AD was root 72, which will be root 72 over 4, which will be root 18. And therefore the height will equal root 99 squared minus root 18 squared, all square rooted, which is simply root 99 minus 18, which gives me root 81 and hence 9. For the position vector of E, you can recognize that AE is the same as CD. They're the same vector, and therefore E minus A will equal, well, D minus C, but remember we have it from before. We've got 4 minus 4 minus 2. And so E is going to be 4 minus 4 minus 2 plus A. That's the position vector of A. So all the way back to the top, that's minus 2, 3, minus 1. Which will equal 2 minus 1 minus 3. We have one more part to go. And we're told that a second pyramid identical to P is attached by its square base to the base of P to form an octahedron. We're asked to find the position vector of this other vertex of the octahedron. So I've got my square base, and I've got my point at the top, which remember was B, and then I had A. I can't remember if I had C and D next. So yeah, oh yeah, D was along a diagonal, and then this was E. Now we're adding a second pyramid underneath, and it's also going to connect all these points. And we want to find the position vector of this point, which I'll call G. Don't forget, we also have this point here that we've been using a little bit anyway, which I've called M. So I'm just thinking about how I can get this. Remember, I've got the origin over here. Well, I've got BM that I can maybe use, and that is going to equal, or two lots of that is going to equal BG, which is G minus B. And therefore G, the position vector, is going to be 2BM plus B. That's it. Essentially, I'm getting from O to B, and then I'm going along two lots. So we just need to work out BM. Well, BM, okay, I don't know that point. How can I get from B to M? Well, I could go from B to A, and then from A to M. But A to M is actually going to be a half of A to D. Actually, at no point have I worked out the position vector of M, which I could do. And in one of the previous parts, if I was working out, I can't remember, oh, it was when I was working out the height, I could have also have used that. I could have worked out BM already, which I've not done. I did it a slightly different way by drawing a triangle, but you might have done it that way. So BA is minus AB, and I'm just going to look at my notes now as I'm writing it, but it should get minus 7, minus 5, 5. And I'm plussing half of AD. Well, AD was 8 minus 2, 2, so it's going to be 4 minus 1, 1. Which is going to give me minus 3, minus 6, and 6. Therefore, G will equal 2 lots of that. Minus 6 minus 12, 12. Plus my position vector for B, which I have not got written down. So 5, 8 minus 6. And therefore, I'm going to get minus 1, minus 4, and 6 as my answer. That might not be the only way we can do it, but it's a solid way, and I hope I've made sense with it. So we're trying. Yeah, we know about B to M, or we can find out about it. We double it to get B to G, and then we can just manipulate the vectors to be able to find this position vector of the other vertex. Okay, well done.